So, hi everybody. Today we are going to be going over fuzzy logic and fuzzy inference systems to help everybody get up to speed on one of the methods you're going to be utilizing in the Explainable Fuzzy Challenge in order to create your AI agent to play Asteroid Smasher. So before we get into fuzzy logic and fuzzy control systems, I do want to remind everybody that if you are looking to register for the competition and you haven't done so yet, you can go to our website here and click on this link and it'll take you to the registration page where it's just a small form you fill out. So registration is still open. We're still looking for some more teams. So please, if you're interested, go ahead and register. It's, that you're not committed necessarily, but we want to get an idea for how many teams are planning to participate throughout the year. I do also want to say that if you are going to register, if you've already registered, please join the Slack channel. So you can join the Slack channel, which is at this location. And that is our primary means of communication with the teams. And plus you can directly message us, get help. You can also communicate with other teams, seeing if other people have questions, and you can collaborate with other teams as well. So I recommend joining the Slack as soon as possible. But regardless, let's go ahead and get started with fuzzy systems. This is some material that was originally prepared by Dr. Kelly Cohen at the University of Cincinnati, but we'll have some additional material after this, including an introduction to fuzzy trees. And then also at the end, I'll be doing a demo of a particular Python module for fuzzy called skfuzzy, and then also how to implement that in Asteroid Smasher. There will be another milestone assignment at the end of this. It will be due on October 3rd. Although remember that you're not submitting anything to us. This is really just a way for you to measure your progress as we go through the competition to make sure that you're staying on track. So without further ado, let's get into fuzzy itself. I'm actually gonna start on this slide. So when we talk about fuzzy logic, what we're talking about is essentially an extension to Boolean logic. Boolean logic is where all the variables are represented by only having two possible assignments, true or false. Fuzzy extends that such that it's on a continuum between true and false, or 0 and 1, such that it can take on any value in between, and how it does so is governed by particular functions. So let's think about days of the week and whether or not they are a weekend day, or do they belong to the set weekend? So if you asked somebody, is Saturday a weekend day? They would say yes or true. Everybody knows that Saturday is a weekend day. That's no surprise. It's completely a weekend day too. You don't have any work that day, and you don't have work the following day. Is Tuesday a weekend day? Well, most decidedly not. You typically, in a typical work week, Tuesday is not only a work day, but is preceded by a work day and followed by a work day. However, would you say that Friday is a weekend day? Yes or no? If you had to say that it was a weekend day or not, fully a weekend day or fully not a weekend day, you would probably say it's not a weekend day. But however, it does have elements of a weekend day. Like you don't have to work the following day. It's typically you're leaving work earlier, potentially you're doing things besides working Friday evening or getting ready for the next day. So it might be more useful to represent that overlap with a different type of system rather than Boolean logic. Fuzzy logic is one way to do this, where you can describe its membership in the weekend set on a scale from 0 to 1 rather than just 0 or 1. And so one answer that you might get from that is, well, it's 0.8. For the most part, it's a weekend day, but not completely. You still have to go to work for the first part of the day at least, or maybe through the afternoon. But then you also are doing other things that evening that are more weekend-ishness, or have more weekend-ishness. Similarly, if you ask somebody if Sunday's a weekend day, well, mostly, it's, in this case, maybe we would say it's 0.95 a weekend day. And that's because, you're getting up, you're doing your weekend stuff throughout the entire day, but at the end of the day, you're getting ready for Monday, you're getting ready for the entire work week. And so it's not the same, you don't have the entire evening to do just anything that you want. So it's still mostly a weekend day, but maybe not completely. And so fuzzy allows you to give these values in between completely true or completely false. This is a visualization of that concept where on the left we have the Boolean or classical logic representation. And so on the this scale we have weekendness, describing how much the days, what weekend value they have. And then simply the days of the week. You can see that Thursday and Friday have no weekendness, Saturday and Sunday have full weekendness, and Monday has zero weekendness. In the fuzzy version, where we're able to go to any value in between 0 and 1, well, we might say that Thursday has a little bit of weekendness. There are a lot of events that happen on Thursday. Maybe there are more and more people not working on Friday, so maybe Thursday evening for them is the new Friday evening. But even then, Friday is even more of a weekend day because typically people are working shorter hours. There are a ton of events on Friday, and you know that you don't have to work on Saturday, so it's much higher. Saturday is a full membership in weekendness, and Sunday, like we said, maybe that's not full membership in weekendness, but pretty high. And then Monday, of course, it goes completely back down to 0. Monday is definitively not a weekend day. So this is sort of the idea of not just fuzzy logic, but multi-valued logic in general between 0 and 1. But fuzzy allows you to do even things beyond this. So the functions that describe your weekendness, on the left-hand side, we have this visualization of a function that describes it for the Boolean or classical case. And we see that there's a discontinuity in between Friday and Saturday and Sunday and Monday. And so this is, on this continuum, this is when you transition from the week to the weekend, or I should say from not the weekend to the weekend. So up until here, it's not the weekend, and then immediately it just becomes the weekend with full membership, and then it becomes not the weekend anymore. Well, as we saw, that might not be the best way to represent things. So what if we had a smoother function that could describe those values in between? And so this membership function, which is a function that describes your membership in a particular set. Now, in this case, we're describing membership in this set of weekendness. And so this membership function maps those values of days of the week to weekendness. And we can see that it smoothly rises up. You're gaining more and more weekendness as you get closer to Saturday and Sunday. And then it drops off pretty sharply to come back down on Monday. And so this is the difference between fuzzy logic and Boolean logic. And in particular, this shows a visualization of a membership function in fuzzy logic versus a membership function in Boolean logic. Now, in most cases, you have more than one membership function. And we'll then see what happens when you not only want to describe something using fuzzy logic, but then you want to use that to do inferencing or maybe decision making or a control action. So we can also do something similar for seasons. So in this case, we have multiple sets. We don't just have the one set of weekendness. We have sets describing spring, summer, fall, and winter. And we can see the same sorts of things if we were going to try to describe the seasons with Boolean sets. Let's say you only went by calendar. Let's say that calendar was the only thing you cared about for defining the seasons. And so you would say that, on September 22nd or 21st, whatever it is, you immediately transition from summer to fall. Now, we know that that's not really how things work. Maybe some people would argue that here in Ohio, that's how it works. The switch gets flipped and it's immediately fall and you get changing weather. But generally, there's more of a gradual change where, it's not just set on the calendar date that it's completely fall. It still has properties of summer and properties of fall. And so maybe a Boolean description of the change in seasons doesn't fully capture that transition. And so on the left, we see these Boolean sets describing those instantaneous transitions. And on the right, we see that there are fuzzy membership functions that have overlap. And so depending on the time of year, you may get contributions from multiple of these. And if these are true normal distributions, you'd actually have contributions from all of them at some point. And so this is how you can handle representing membership in multiple sets potentially at the same time. And then what you do with that, you can then do inferencing with that after the fact. So why is this valuable? In particular, fuzzy is somewhat representative of how humans think, where humans aren't doing precise calculations and coming up with exact models to do predictions. We often do this with very vague concepts with these linguistic labels that we're able to somehow take in and reason about at a high level. And that's valuable because it allows you to deal with the uncertainty in the world to a greater extent. So this is from Bart Costco in his works called Fuzzy Thinking. And he's described a lot of this where he says, oftentimes one reasons with scant evidence and vague concepts, rules of thumb and tentative facts, we're not getting exact explicit sensor data in, and your brain is crunching numbers similar to a computer, at least not explicitly. You also deal with hunches and beliefs, estimates, guesses, all these things, and humans are still able to reason about these things using the same type of process. Natural selection evolved with this uncertain cognitive calculus. Pretty much everything that is alive has had to evolve with these uncertainties and develop strategies that still work even with these uncertainties. He also says that while we employ the products of exact science as decision aid tools, even things that we're doing with machine learning and other things like modeling and dynamic system control, the final control remains fuzzy, meaning that we're not getting rid of that uncertainty, and so you still have to deal with it in some ways. Okay, I'm going to skip ahead a little bit. So a few fuzzy statements. These are things that some famous folks have said about fuzzy, not just fuzzy logic, but mainly dealing with precision and uncertainty and how you resolve that. And so Henri Matisse said that precision is not truth. You can be more precise while not being more accurate. Sometimes the more measurable drives out the most important. That can definitely happen when you focus on what is easily measured versus what actually has the most impact. And Einstein famously said, so far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. And he was really talking about the innate uncertainty in the universe. And fuzzy is a way to deal with that in a practical way. We can't get around it. So we may need to develop methods for doing so. And famously, Lottie-Zada, he's the father of fuzzy logic. He originally came up with the idea back in the late 50s, early 60s, I believe. Said that as complexity rises, precise statements lose meaning and meaningful statements lose precision. So a lot of people talking about the importance of being able to handle uncertainty. And then, fuzzy really offers a way to do that. So fuzzy's origins, invented in 1965 by Lottie-Zada. And it has the ability to deal with situations in which you may not be able to make a sharp distinction between the boundaries. It's unique in that it's able to simultaneously handle numerical data as well as linguistic knowledge. It is often, not always, but often a nonlinear mapping of input data into a well into output data. It's not necessarily a vector into a vector. You can have multiple outputs, but in many cases we have a feature input, a vector input to a scalar output. I'm actually gonna skip ahead a little bit to hear some of the motivations behind fuzzy logic. Alleviates some of the difficulties in developing and analyzing complex systems encountered by conventional mathematical tools. Because of the labels that we can assign to those membership functions that describe the sets that we saw a little bit earlier with things like the seasons or weekendness, we can then use those linguistic labels and reason about them in a very human way by doing inferencing with them. And we'll show some concrete examples in a bit of what we mean by that. And observing that human reasoning can utilize concepts and knowledge that do not have these well-defined, sharp boundaries. This is a general notional plot of the precision versus the complexity for different types of methods for modeling of systems. So on this end, notionally, you have mathematical equations, so explicit mathematical equations, which generally have extremely high precision the more complex the system becomes. You can also have model-free methods, which don't ramp up the precision nearly as high, and fuzzy systems, which keep the precise statements relatively minimal as the complexity of the system increases. And so this really becomes beneficial for complex systems that are difficult or impossible to model, systems that are controlled by human experts, or systems that use human observations as inputs, because humans typically describe things in a very vague and uncertain way. And then we also use natural language to describe it, which is also vague compared to mathematical statements. And systems that are naturally vague. A lot of times in the behavioral and social sciences, there's been work applying fuzzy logic in that regard. I know that in particular, Professor Jerry Mendel had done a lot of work where they were actually modeling language with fuzzy sets. They were specifically assigning fuzzy membership functions to words because that was able to better capture the distribution of meaning behind that word to different humans. And so you then had this representation of what the word actually meant, the semantic meaning of that word to people in general. So situations like that, fuzzy is extremely valuable. But it's valuable in other situations as in dynamic control, AI and machine learning problems, all these sorts of things. I do want to highlight that fuzzy logic and probability are different. Many people confuse them because both have degrees of, both give you values representing set membership in different ways between 0 and 1. However, they are not the same thing, and it's important not to confuse them. The difference is that probability is prescriptive and measures the likelihood that you'll fall into a Boolean set. That event being a Boolean set, true or false, that is the probability is talking about how likely it is that you fall within that Boolean set. Whereas fuzzy is describing, and by the way, that's a future event. Fuzzy is measuring something that has already happened. It has happened, you're taking a measurement, but then the uncertainty is how much you belong to a particular set, which may or may not be Boolean. That's the difference between the two. I'm gonna go ahead and skip over this. This is another comparison between crisp and fuzzy sets. When we say crisp here, we simply mean Boolean. So one thing you could represent with fuzzy sets and a Boolean set is height and whether that represents tall or short. So in this case, this Boolean set is representing tall. And so at 180 centimeters, we're saying that that is when someone is considered tall. We're assigning that label. That's what this membership function is labeled. And so, that's what this set is labeled. And so if we look at this membership function, once we have 180 centimeters, we're just completely in the tall set. And if you're below that, you're in the short set. However, we can have a degree of membership if we have this sigmoid-looking function that describes your tallness and shortness on this continuum. And we could say, well, in this case, if we're 180 centimeters tall, well, we're 74% tall and 24% short. We have contributions from both. And if you're 179, you get this distribution of tall and short. So instead of just having this this drop off, it more accurately represents the concepts of being tall versus being short. We've already seen some visualizations of membership functions, but to give some more concrete definitions, this is the function that embodies the mathematical representation of membership in a fuzzy set. So if we go back one slide, this membership function is describing your membership. Actually, in this case, it should only say tall. You know, we're measuring the membership in the tall set. And we see that as it's increasing as you get further to the right. Ideally, we would have another membership function that would describe your membership in the short set. However, what we're doing here is simply saying that if you're not in the tall set, the complement of the tall set is the short set. So 1 minus tall is short. But normally you would have a separate function describing your membership in the short set. The common notation used for fuzzy membership is mu, the symbol mu. The subscript in this case is the fuzzy set that you are measuring the membership in. And this is the input value, the value of who you are measuring the membership. And so in this case, if X was equal to 180, so that would be our input value X, mu of tall, so mu sub tall would be 74% or 0.74. So that is that nomenclature is how you would represent that. You'll see this in a lot of the literature and also maybe some of the documentation that we use throughout the competition. I'm going to go ahead and skip over this. Some common membership functions, though. Triangular is extremely common. Trapezoidal is also very common, and Gaussian functions are very common. They all have different properties, and so you may want to use different ones in different situations. You know, if you have a situation where you want a continuous output, maybe you go with Gaussian membership functions. If you have cases, though, where you don't know much about the system and you want to keep it simple, maybe you go with triangular. Maybe go with trapezoidal if you want to extend some of the triangular behavior. But that's not the only types. There's other types like sigmoids and polynomials. There's all sorts. You can even make your own irregular membership functions. Remember that, you know, there's very few constraints on the membership function shape, except it has to fully describe the membership of that measured value in that range, in that domain of the input space. So we already saw the representation of tall with what looked like a sigmoid membership function. Now let's look at the range of height in centimeters again, but with multiple membership functions for short, medium, and tall. So these are all different sets that have different functions that describe the membership in each of them. And so in this case, short is trapezoidal. So if we're below about what looks like, I don't know, 158 centimeters, we have full membership in the short set. So at that point, we would say that someone is just short. However, in between, like 158 and 163, something like that, we see that there are contributions from both the short and medium sets. And so we won't have full membership in either one, but we'll have some in-between value. And then if, you know, in between about 163 and 172 centimeters, we're completely in the medium set. And above about 177 centimeters, we're just in the tall set. So trapezoidal does allow you to still have full membership over different ranges in the input space. while also allowing for contributions from multiple where they overlap. An example with triangular membership functions, if you have some health index, maybe you have different sets representing the level of healthiness of somebody. So in this case, we have 3 triangular membership functions, and they describe healthy, less healthy, and unhealthy. And you can see that you'll get contributions from 2 of these at any point, starting at 0.25 up to 0.75. But then outside of that, you just get contributions from the 1 at the boundaries. And then outside of that, we don't have any contributions. So these are some examples of how you might want to represent your input spaces, or the range in your input spaces, using multiple fuzzy sets and different membership functions to do that. Boolean and fuzzy logic operations, you have some of the same operations like conjunction and disjunction. You also have the complements. We'll talk about a little bit of these later. We'll talk about these a little bit more later, but the idea is that you have the same sorts of operations. So in this case, conjunction. If you're representing A and B, this is what you would have. Sorry, A or B. This is what you would have in the Boolean sets in this visualization. You can then represent that with fuzzy sets, fuzzy membership functions. And you can see that it's shaded because all values that are in A or B are what you're looking for. Similarly, if you're looking at A and B, you know that this overlap is, in the Boolean case, is where that's happening. In the fuzzy case, well, you can also see where they overlap, and so you get this representation of A or B. And if you had the complement of A or B, so not A or B, you would have everything outside of the A and B sets. And in the fuzzy case, it would be this shaded area, which is the complement, so not A or B. There are a number of things you can do for combining and reasoning about membership functions, you know, doing these operations with fuzzy logic as opposed to Boolean logic. One of these are also called T-norms in the literature, but fuzzy union, so A or B, the membership is considered the maximum of the membership values in A compared to the membership values in B. You can also look at fuzzy intersection, or A and B, which is sometimes the minimum of those values. You'll also sometimes see the product here if you're looking for a continuous output, and the complement, which is simply just 1 minus the value. This is how some of the operations on fuzzy sets relate to Boolean logical operations. This is just a visualization showing some of the same things. We're going to go ahead and skip that. So now we're going to get into fuzzy inference systems and fuzzy logic control. So this is a block diagram of a typical fuzzy logic controller. So what happens is that the inputs get fed in. You have a fuzzification interface where you fuzzify all the values. And what that means is that the input values get assessed to find their membership values in each set. You then have a knowledge base that, or an inference engine. And what that is a bunch of rules that dictate, given the active input membership functions, what the active output membership functions will be. So once you identify the active output membership functions, there are multiple of them active typically. And so you then have to resolve them by defuzzifying them, that's what this word means, into a single crisp output. And then that output gets fed into some system with some dynamics, some data gets fed back, gets passed through your sensors, and then comes back again. So this is just a traditional dynamic system feedback loop with a fuzzy logic controller inside of it. And we'll see some actual examples of what this looks like in a little bit. So let's say that you had a heater and you wanted to control the output of the heater using fuzzy logic. So the idea is you want to write the control actions as fuzzy logic rules. So in standard logic, you might say something like, if the temperature is less than 68 degrees, then turn the heater on. In fuzzy logic, this would be different because instead of saying it like this, you would just say, if it's very cold, which is some function of temperature, then more heat, which might correspond to turn the heater on. But this also has embedded in it a notion of not just turning the heater on, but turning it on to some extent, or turning it on for a certain amount of time, things like that. But remember that we're dealing with these linguistic fuzzy representations, not explicit values. And so in this case, okay, guess we're not. I thought we had another example with the heater. But in this case, we're going to represent all of our output actions with these linguistic rules. As we saw, the sensor, in this case, the sensor is reading the temperature that gets fed in. It gets fuzzified. These rules, which very cold is a label on one of these input sets, then more heat, which is an output set. The inference engine is constituted by the full set of these rules that dictate the input to output relationships. Then once you have multiple of the output sets active, you resolve those into a final output action that gets sent to your system. And in this case, it would either be a turning the heater on or not, or if there's some graduated if it's more granular than just on or off, it would be the amount that you're turning the heater on, for instance, the amount of energy. Okay, we've already seen that. This is a visualization of what actually happens when you have multiple inputs and what the T-norms or the logical operations are doing. So in this case, let's say that our rule was saying if if X was in this set, whatever that set is, and Y is in this set, whatever that is, then our output is in this set, in the output space. So then what happens is we do fuzzification, and so we get these membership values. This is the value for X. So this is an input. We get the membership value in that set, which is this value here. And then we also do the same thing for the input Y. We get the membership value in this set. We then need to resolve those somehow. So we do and, we're saying if X1 is in this set and Y is in this set, then this set, but the contribution to that set makes is the minimum of these two values. And remember that it's the minimum because that is the logical operation for conjunction in fuzzy logic. It's one of the options at least. And so we'll take the minimum. That value is then the strength of that rule, and that affects the output membership function. In this case, we're truncating the output membership function at that point. And so we get this contribution from that output membership function. We then have another rule because we have other membership functions that X and Y fall within. And so we do the same thing with those. We get the two membership values for the two membership functions. Then that rule is saying that this membership function is active on the output side. And we get this rule strength from looking at the minimum of those two input membership function values. And then we scale the output, well, in this case, truncate the output membership function at that point. So these are the active rules. We have our active membership functions, their contributions, they're being truncated with this function of the input membership function or the input membership values. And then we get this resulting distribution that we then need to resolve into a single value. And that is called defuzzification. So there are multiple different ways to do this. But let's say, for instance, that we wanted to take the center of area or center of gravity. We can look at that distribution and calculate where that is, and then that will be our final crisp output from our control system. So this is another example where we're saying, actually, I'm going to skip this example. Let's go to this example. So in this case, this is an example of a fuzzy inference system for determining the risk of somebody based on their age and the amount of car power that they have. Now, this might be used by an insurance company to measure risk, or to predict risk for different people based on their age and the power of the car that they have. So one rule that you might have, and first of all, let's say that you have membership functions describing age for maybe young, normal, and old. And then you have car power membership functions, let's say low, medium, and high. And then also for risk, you have sets describing low, medium, and high. So one rule that you might have is if you're young, if you belong to the young set and your car power is in the high set, well, that should correspond to high risk. And that seems like it makes sense, right? That's something that humans intuitively seem to know. Even if they didn't know, this could still represent the system just fine, but that intuitively makes sense. We can make this simply by hand by representing these concepts. We could also have another rule that says if your age is normal, so you're not young and you're not old, and the car power is medium, it's not low, it's not high, then your risk is medium. It's also not low and not high. And so we can go through and do that for every combination of age and car power and get an associated risk output with that. And then we can also evaluate actual crisp values for that to get crisp outputs. So let's look at an example for both of these rules. So let's say that your age falls here. You're not completely in the young set, you're not completely in the normal set, but you're somewhere in between. So in the first rule, this is the value for age. We get the membership value in young, which is 0.8. We also look at the membership value of car power, which is in high at a membership value of 0.4. We then know that because of our rule, if you're in these two membership functions, your output membership function is high, you have high risk. Looking at the other rule, we see that normal and medium are activated for age and car power, and that means that our risk is medium. And we also get the membership values on the input side. We can then use those to calculate the truncation points for high and medium risk, because those are the two active output membership functions. If you remember, we're taking the minimum. So in this case, the minimum of 0.8 and 0.4 is 0.4. So we'll be truncating the high membership function on the output side at 0.4, and we'll be truncating the medium output membership function at 0.3. So let's go to the next slide. We can see that here. We're then using both of those truncated output membership functions, our aggregated output, and we're going to then resolve that to get an actual value out for the amount of risk. And let's say that we took the centroid of that, maybe we decide that the risk is here. It's pretty high. It's not completely medium, it's not high, but it's you're getting contributions from both of those. There are multiple different ways to do defuzzification. One of the most popular is center of gravity. There are also several approximations for doing this out there in the literature. These are by no means the only ways. There are all sorts of ways to defuzzify that distribution. But really what you're trying to do is resolve this aggregate into a single value in a way that makes sense. And there are different properties for different defuzzification methods. They may lead you to having discrete output spaces or continuous, but different properties. It really depends on the properties you're looking for, the properties of your system, etc. But generally, a good place to start is with center of gravity or some approximation of center of gravity. Okay, so that was fuzzy logic and fuzzy inference systems at a pretty high level with some examples. One of the issues with fuzzy inference systems in general, though, because of the fact that you have to describe the every combination of the membership functions on the input side to create your rule base, if you're using conjunction to describe your antecedents, meaning if you're saying, if x1 is in blank and x2 is in blank, that means that the rule base will increase exponentially with the number of inputs. And so because of that, fuzzy inference systems don't scale well if you have a large number of inputs. So one way to mitigate that is with what's called a fuzzy tree. Fuzzy trees are an extension to cascaded fuzzy systems. So let's get into that a little bit more. Fuzzy logic in general has been hybridized and structured in many different ways. The primary intent of cascaded and tree structures is to mitigate those scalability concerns that we mentioned. And the optimization methods are interchangeable between fizzes and cascaded or fuzzy trees, so long as they can tune multiple fizzes worth of rule bases and membership functions. So we're going to hear more about this next week, but when we look at the progression of genetic algorithms and fuzzy inference systems being used together, genetic algorithms were first used to optimize other problems, and fuzzy inference systems were used as approximators. They were then combined to allow genetic algorithms to tune the parameters of fuzzy inference systems to create genetic fuzzy systems. Then after that, genetic cascaded fuzzy systems were introduced. This is where you have a number of fizzes in sequence, and the GA is optimizing either the fuzzy parameters or the location of those fizzes or both. And then the genetic fuzzy tree is a further extension of that, where there is no necessary notion of directionality. So any of the fizzes can be connected to any other fizz, and you can have things like recurrence and other approximators or other functions included in that system. So in general, this is what a cascaded fuzzy system looks like, where you're taking in crisp data, you're feeding into one fizz. The output of that gets sent to another fizz, and by the way, you may have crisp data coming into the other fizzes below. But the important thing is that the output of one fizz is being used as the input to a subsequent fizz. The architecture, this is the most basic architecture possible, where you just have, one output getting fed into the next fizz, and then, some other potential input data. And then you get a final control output at the end of that. This is by no means the only or typical architecture of a cascaded fuzzy system. You may see multiple fizzes with their outputs getting fed into a single fizz at the next layer, and so on. But this is the idea. It hierarchically breaks down the problem. The benefit of this is if you have a large number of inputs, it really decreases the number of parameters that you have to specify in terms of the rule bases. However, the performance is bounded from above by a single fuzzy system that takes in all of the inputs to one fizz. However, you may not have the same approximation capability per parameter. So in general, cascaded systems are more efficient at finding approximations per parameter than a single fizz, and even more so for a fuzzy tree. And so it allows you to get richer approximations for the number of parameters that you have to specify. If no coupling between the variables exists, you can achieve the same theoretical performance as the single fizz, but with far fewer parameters, which is similar to what I was previously talking about. So that is a cascaded system. A fuzzy tree simply removes that directionality or other structural assumptions of a cascaded or hierarchical fuzzy system. Again, feedback is allowable in a fuzzy tree. You can also hybridize with other elements. So in this case, we see this tree-like structure of a bunch of different fizzes. The outputs from multiple FISs are getting fed into FISs below them. They don't necessarily need to be below them. You may have a situation where the output from, a FIS here is getting fed into this FIS over here. That is completely allowed. You can also have the outputs being fed back in as recurrence. The big benefit of this, again, is that much richer approximation for the number of parameters that you have to specify. Additionally, if you're creating this by hand, it allows you to preserve explainability. And what I mean by that is you can preserve the semantic meaning of the input-output relationships and the labels associated with them. An example of this, this is from a system that was created for beyond visual range air-to-air combat between multiple vehicles. This is an example of part of a branch of a fuzzy tree that was taking in multiple different sensor information to actually decide if it would bid on firing a missile in particular situations. Again, this isn't necessarily relevant, except for the fact that this structure preserves that explainability because each of these outputs has a semantic meaning, a human interpretable semantic meaning. And so, in this case, the name of the FIS is also where we're considering the name of the output. So let's say that you wanted to determine if you're going to bid on firing a missile in this situation. You may want to know, well, is my effective range such and such? If my effective range is this, then that informs my turning range. That informs my range of accuracy. That, in combination with the effective azimuth, the angle, determines my missile capability. And if my missile capability is adequate and my missile need is high, well, then maybe my fire bid is high. Maybe if my missile need is low and my missile capability is low, then my fire bid is low. And so it's very easy to see how you can directly construct one of these systems for a very complicated subproblem in a situation like this. This also allows you to audit the system due to the inherent explainability of fuzzy systems. And so what these fuzzy trees allow you to do, if you create the structure yourself, is rapidly create a structure based on expert knowledge, if you have any, and keep human interpretability while also potentially getting high performance without knowing much about the model, or the system dynamics, I should say. This can also, of course, be combined with machine learning methods where you're learning maybe the structure, but definitely the parameters that are inside of these. And so that is the power of fuzzy trees combined with things like genetic algorithms or some other machine learning process to both encode the expert knowledge that you do have, if you have any, encode the structure such that it's human readable and interpretable, but then also leverage that in conjunction with machine learning methods to then find the optimal, or the best parameters that you can for your problem. So that is fuzzy trees. One reason why we went over this is we highly recommend this methodology for developing your AI agent. Now what I'm going to get into is a quick demo with a particular fuzzy package for Python called skfuzzy. So skfuzzy, you can read about it at this website on pythonhosted.org. It has a bunch of examples. I'll show you one example, which is pretty common, called the tipper example. So the tipper example, let's see. The tipper example goes through the creation of a FIS for determining how much you should tip at a restaurant based on service and food quality. This is a pretty classic fuzzy example. The MATLAB toolbox has a similar example if you look it up. However, we're going to look at implementing this in Python and then how we can do that with Asteroid Smasher as well. So instead of doing this, going through the example on the website, I've already got this in Python, so let's take a look at it. By the way, we don't prescribe that you use skfuzzy. This is just one option for a fuzzy toolbox. There are other options out there. You can also write your own. We fully encourage that. It may be higher performance. You may be able to do more specific things that aren't included in skfuzzy, that sort of thing. So this is just one option. So here what we're doing is we're telling it that we have one antecedent, so one input named quality. Well, this is the variable, this is the name that we're giving it. And in this case, it's in the range from 0 to 10. We also have service from 0 to 10. And our output, the consequent, is the tip amount. And this is going to go from 0 to 25. 25, in this case, it's a percentage. That's where our output is going to be limited to that. And then what we're going to do is we're going to generate our membership functions. Now, in this case, there is a built-in automatic membership function generator. It'll generate these triangular membership functions to fill the space, and it's creating 3 of them for each input. We can also specify the the membership functions. We can specify them directly by calling that variable. So in this case, we're doing the output membership functions. We could do this for quality and service as well, simply by doing, let's say we have a membership function called low. We can do the same exact thing. But in this case, we're just doing the output membership functions manually. And so we're doing a triangular membership function. That's what this is. We're giving it the universe of discourse, which is basically the range. It's the range information about this variable as defined here. And these are the points of the triangles. So in this case, this is a triangle with the center point and leftmost point at 0, and the rightmost point at 13. So this is a right angle triangle. We also have medium and high. These are defining the leftmost, the center point, and the rightmost points of the triangles. So let's go ahead and evaluate that. We can then take a look at the average, which, by the way, it makes the automatic membership functions that it makes for quality and service are, I believe, poor, average, and high, if I remember correctly. But let's take a look at this. This is the quality input, and this is the average membership function being highlighted here. We can also see the poor membership function and the good membership function. And service will look similar, but let's go ahead and take a look at that too. So this is service. Remember, we did the auto MF, so it just did triangular membership functions that are distributed in the space. So again, we have poor, average, and good. We can also take a look at our output membership functions. And remember that we gave them these labels, low, medium, and high. And you can see the definitions of the triangles as we have here. That's what that looks like. So next we have to define our rule base. In this case, we're adding a rule called rule 1 that we're saying if quality is poor or service is poor, then the tip is low. So we're associating the input membership functions with the output membership functions. We have another rule that says if the service is average, then the tip is medium. And we have another rule that says if the service is good or the quality is good, then the tip is high. And so we can define our system using only those 3 rules. In this case, we're using not just conjunction, but disjunction. In our control systems, we're using conjunction. So you do have to define every combination of input membership functions. But let's go ahead and add those to our FIS that we're creating. So let's go ahead and look at rule 1. Oh, maybe. Oh, maybe we can't do that while I'm in scientific mode. I guess not. Oh, that's okay. Well, let's go ahead and create a fuzzy control system using our rules. And then we'll create a control system simulation using that control system. And that allows us to evaluate the FIS for different values. And so what we can do is we can assign these values to our inputs for quality. We're going to say quality of 6.5 and service was 9.8. We can evaluate and compute the output based on that. And not only can we get the output value, so this is going to show us the output from our FIS. So when quality is 6.5 and service is 9.8, we're saying that we should tip 19.84%. So pretty good, a pretty good tip because our service was very high. We can also take a look at what that looks like in our FIS. So this, remember, our aggregate that is formed by truncating our output membership function values. So our rules are determining where to truncate these output membership function values at based on the input membership function values. We see that we have high and medium active, and high was contributing quite a bit. Medium is contributing a little bit. And so then when we do the defuzzification to get the centroid of that, or the center of gravity, that winds up being right here at this location, which winds up being the value of our tip output. And so that is creating a fuzzy inference system and evaluating it with skfuzzy. Now let's take a look at how you might do that in Asteroid Smasher. So remember in Asteroid Smasher, we have to define our fuzzy controller using the actions function inside of the fuzzy controller class. The fuzzy controller class inherits from this controller base class. And so the two things you have to have are this name property and the actions property. Sorry, the actions function. And so what we're going to do is define a FIS and then use that in some way. So we have our initialization of our fuzzy controller class, and we have this function called construct FISes that runs when you initialize. And so this construct FISes function, we're going to make a FIS like we just did in skfuzzy. So we're importing everything from skfuzzy that we need. And we're going to go through and make our first input, which we're just calling input 1. We don't know what it is right now. That's fine. We have another input called input 2. And we're doing this. They'll have a range from -1 to 1. And we also have turn rate being the output. So this is the consequent. This is the output from our single FIS that we're making right now. We're then going to define all of the membership functions for our inputs and output. We're not going to auto-generate them, but this is where you could do that. So we're saying that input 1, negative, is from -1 to 0. Input 1, the 0 membership function, is from the entire range, -1 to 1, centered at 0. These are triangular membership functions, by the way. And then we have positive going from 0 to 1. We have the same thing for our second input. And we have the same thing for our output. So we have our membership functions defined. Now we need to define our rule base. Since we have 3 membership functions for our first input, and we have 3 membership functions for our second output, or second input, we will have a rule base of size 9 because we have to define every combination of these. So 3 times 3 is 9. If we had a third input, we would have to define 27 because we would have 3 raised to the third power. So this is our rule base where we're going through and we're looking at each combination of input membership functions. We have negative for input 1, then 0 for input 1, positive for input 1, and then iterating through for input 2. And then we have the associated output actions for each of those combinations. These were just handmade. They don't mean anything necessarily. We don't even know what inputs were being given right now, just some value. So we don't really care what these are. They're just essentially random. We then create this rules list and pass it to control system to create our FIS1 controller. We're then going to create a control system simulation so we can actually evaluate this FIS by passing it input values. And so we're storing that here in our fuzzy controller class. We're then going to evaluate it in our actions function. This is where all of your actions happen that determine your outputs. Your outputs being the turn rate for the ships, the thrust, and whether to fire a bullet or not. And so in this case, we're going to get some sort of information from asteroids, which remember is an input data, which is a dictionary. So we're going to grab the asteroid data. We're just going to assign it to this asteroid variable. And we're going to use some information from the asteroids as our inputs to that FIS. And think about what metrics you may need to calculate in other places in order to create your AI system. So let's say you wanted to calculate something like get the closest asteroid distance. That could be something that you would want to pass in to your fuzzy system or use as maybe some other metric or in combination with some other metric to calculate something else that then becomes an input to the system. There are lots of options here, but let's say that you wanted to take in something like the angles. So you wanted to get the closest asteroid distance and the closest asteroid angle, and then you do some other things, and then the sum angle is what you're putting into this FIS. So in this case, what we're doing is we're simply looking at two asteroids, and we're looking at the asteroids angles, which in this case is in your global frame. That is the input to our FIS. For inputs 1 and input 2 are the angles. These are being normalized. Remember, they're from -1 to 1. So we're normalizing them because the range of angles is -180 to 180. We're computing the output based on that, and then we're grabbing that output. Remember that we need to scale it by 180 because the turn rate goes from -180 to 180, but the output from the FIS is only from -1 to 1. So we're scaling it by that to map it onto the right ranges. And that output is then going to be our turn rate. So our turn rate is the output from this FIS, which is based on inputs being angles of asteroids, but they could be anything else. You know, they could be, let's say that we were calling our get closest asteroid distance and get closest asteroid angle. You know, maybe in that case, instead of having just the angles be inputs, we would want the input to be, you know, closest asteroid angle, and this would be closest asteroid distance, and then based on that you output a turn rate. But in this case, we're just using the angles themselves, but we can evaluate this and see what that looks like. So remember that these rules are essentially made up, so it's not going to have any sort of good behavior. It just needs, we're just demonstrating that you can use a FIS in this way to dictate the turn rate of the ship at any given point, or at any given time in the simulation. So let's go ahead and run that. We can see we have 3 ships, and they're doing various things, but we see them all turning. And by the way, it's assigning the same value to these. But we see them turning, and it's going to turn based on the angle of not necessarily the closest asteroid, because remember, we're just grabbing whatever the first asteroid and second asteroid are in the list of asteroids. So that is just random, essentially. We're picking 2 asteroids and basing our turn rate off of those 2 asteroids. And then the other actions that we have, the thrust and the firing of the bullets, are just, you know, random functions, just to demonstrate behavior. Remember that this doesn't have any intelligence built in. It has no idea how far the asteroids are. The only thing it knows right now are the angles of 2 asteroids. But that is a demonstration of how you can get a FIS up and running in Asteroid Smasher. in your fuzzy controller class and use it to actually dictate the control actions of your ships. And so you could create one by hand that might be pretty effective at doing something like assessing threat level of particular asteroids. So maybe you want to run through the list of asteroids and determine which asteroid is the highest threat level. So maybe your FIS output, instead of being the turn rate, is something like threat level. You then use that threat level to be fed into maybe another FIS that determines whether you're going to shoot or turn or apply thrust to try to get out of the way. You know, this should give you a good basis for thinking about how you want to construct your structure of your fuzzy tree or multiple FISs that you're using, along with what metrics you'll need to calculate and the functionality that you'll need to build out to do so. So remember that what we're doing here, one more time, we're in our fuzzy controller class, which inherits from controller base. Within this, you need to define the name of your controller, the initialization function or method in fuzzy controller. In this case, we don't have anything to initialize besides constructing our FISs. And this constructing FISs function is simply creating that FIS. And then we're using that FIS in our actions function to determine the turn rate based on asteroid angles. And so that should give you a pretty good starting spot for how to create FISs and how to get them up and going in Asteroid Smasher. The last thing we're going to talk about is the milestone. So I've already talked about designing fuzzy controllers in Asteroid Smasher. So your milestone is you will be creating a fuzzy tree in Asteroid Smasher. So what you're going to do is create a structure using multiple FISs. You're going to define those FISs. You're going to calculate metrics based on the asteroids or whatever other state information you care about. Maybe you're doing things with the map size, maybe the simulation time, the asteroids, the bullets, other vehicles, whatever you want, but you're going to calculate some metrics or otherwise get input data and create your FISs and get them to evaluate and actually output these control actions to your ships. This is due, quote unquote, on October 3rd. It's really just a way for you to start playing around with Asteroid Smasher and making sure that you can create FISs correctly and get them to actually execute in the simulation environment while using simulation environment data. So yeah, you must take in something from the input data dictionary, and you must control some aspect of the ship based on a fuzzy system output. If you're running into trouble, please message us. The Slack channel is the best way to do so. You can also reach out to us through email. But yeah, so that is fuzzy logic, fuzzy inference systems, skfuzzy, and implementation in Asteroid Smasher. So with that, I will take any questions that anybody has.